In this lecture, I will be talking about simultaneous equation models. Simultaneous models are very peculiar to econometrics. This is because the cause and effect relationships that we have in usual regression models do not always hold in case of econometric problems. Very often what happens is that some of the variables which may be the cause variable in one equation might turn out to be an effect variable in another equation. So, unlike in natural sciences where causes and effects are very well defined, economics and social science models generally have difficulty in identifying which is the cause and which is the effect, and hence what we require is to treat the different variables together in a set of equations known as the simultaneous equation models. What we will do in today's lecture is give you an idea of what simultaneous equation models is and also tell you why we require these models. Why simultaneous equation models? Let us look at regression models. Suppose we have p plus 1 variables and we want to set up a regression models using this p plus 1 variables. Among this p plus 1 variables, we identify one variable y as the response variable or the dependent variable and use the other p variables x1, x2, xp as a set of explanatory variables which would explain what y is. So, usually the x1, x2, xp are assumed prefixed, that is they are known beforehand and they influence the y variable. Now, if you look at this, what we talk about here is that x1, x2, xp is a set of independent variables. These are referred to as the cause variables and they affect the y variable which is the effect variable. So, we have a unidirectional cause effect relationship in this case, and in most natural sciences this is very clearly defined. So, given this, we generally set up a linear model which is the simplest of all models. We can have nonlinear models as well, and in this linear models we have y on the left hand side which is explained by an intercept beta naught plus beta 1 x1 plus dot etc. plus beta p xp and a disturbance term. Now, this beta 1, beta p etc. these are the slopes of the x1, x2, xp independent variables. So, they give us the impact of x1, x2, xp on y. However, very often this well defined one directional cause effect may not be available. So, in cases of economic studies, this cause and effect is not so distinct or clear cut. As an example, we can look at the quantity of a good demanded. Let us look at QT as the quantity and PT as the price of the commodity. Now, we say that the demand function is QT is a function of PT. So, Qt, if you take a linear function, Qt is equal to alpha naught plus alpha 1 Pt plus the disturbance term U1. However, what we are looking at here is that we say that the quantity demanded would be decreasing as price increases in most cases. There are exceptions of course, but that will be given by the sign of alpha 1. But very often what the economists would tell you is that the quantity demanded increases, then what will happen to the price? Will it remain unaffected? Definitely not. Obviously, if quantity demanded increases, then the shopkeeper would be induced to increase his price because he sees that there is more demand for his commodity and hence he can be increasing his price. So, we cannot say that quantity demanded does not affect price. So, now we have a situation where the demand function tells us that the quantity demanded depends on price, whereas in some cases we can have price as the effect variable and quantity demanded as the cause variable. So, the question would be which affects which, and this is a problem which is very peculiar to econometrics and comes in very often when we look at econometric problems. Now, let us look at another problem. We have the demand function as before. So, we have Qt is equal to alpha naught plus alpha 1 Pt plus E1. In addition, we have a supply function where the quantity supplied is given by beta naught plus beta 1 price plus another disturbance term. Again, quantity supplied would depend on what the price is. In this case, unlike demand, the more the price, generally the more the quantity supplied. However, if you look at these two equations algebraically, then the two equations would look very similar to each other, because alpha naught alpha 1 beta naught beta 1 are unknown parameters. So, when we write this down algebraically, they would, except for the change in the sign, they would look exactly similar. Moreover, if we take a convex combination of the two functions, that is, we multiply the demand function by a lambda value which is between 0 and 1 and multiply the supply function by 1 minus lambda and then add these two up, we will end up with Qt equal to lambda alpha naught plus 1 minus lambda beta naught plus lambda alpha 1 Pt plus 1 minus lambda beta 1 Pt plus lambda U1 plus 1 minus lambda U2. Or more simply, we have Qt is equal to gamma naught plus gamma 1 Pt plus U3, where gamma naught is the intercept and gamma 1 is the coefficient of Pt, and U3 is a combination of the two errors. Now, if you look at this convex combination of the two functions, again this looks similar to the first two functions, that is the demand function and the supply function separately. So, the demand function, the supply function and the large number of convex combinations that we can have with different lambda values would look very similar to each other. Let us see what the statistical problems would be with this function. Now, suppose we want to fit the two models. Now, we have the data for this as Pt and Qt. So, we go to the market, get the prices on a particular day T and get the corresponding quantity marketed on that day. We do this for n different days and we get the set of observations Pt Qt for n different days, and then we fit this data, use a regression line and fit the data, use any one of the models, linear models. What will happen is, we will get the slope which is summation t equal to 1 to n Pt minus P bar Qt minus Q bar divided by summation t equal to 1 to n Pt minus P bar square, and we will also get the intercept which is Q bar minus slope times P bar. Now, the question would be, what does the slope stand for? Does it stand for alpha 1, does it stand for beta 1, or does it stand for gamma 1? You may say that if the slope is positive, then it should be beta 1, but then in some cases, very special cases, the demand also increases as the price increase. So, it can also stand for alpha 1 if you have a positive value of the slope. So, we are not sure as to what this Pt Qt data leads us to, the demand function, the supply function or the convex combination, and the same with the intercept. We do not know what the intercept stands for. Does it stand for alpha naught, does it stand for beta naught, or does it stand for gamma naught? So, we have a problem here and this is referred to as a problem of identification. We do not know as to what the estimate stands for. So, these are typical problems that we come across when we look at simultaneous equation models. But at the very beginning of simultaneous equation models, since we are not very sure of which variables are endogenous and which variables are exogenous to the system, we need to define this endogenous and exogenous variables. So, what are endogenous variables? Endogenous variables are variables which affect a system and is also affected by it. So, it both influences the system, that means it acts as a independent variable as well as it is influenced by the system, that is, it acts as a dependent variable. So, it is both a cause and a effect variable. As opposed to this, there will be some variables which are exogenous by nature. Exogenous variables affect a system, but is not affected by it. So, these exogenous variables are primarily independent variables. They do not depend on the system. So, these, if you remember the simple regression model where we had one y and a set of x's, the x's were exogenous variable, but y was not exactly an endogenous variable. We call it a response variable, which is a very special case of an endogenous variable. In that case, the response was affected by the system, but it did not affect the system. So, that was a very special case, but in some cases what happens is that some of the responses may themselves be in some other situations act as a independent variable. In that case, we need to go for a simultaneous equation model. Let us look at an example. So, if we go back to the demand function, we had Qt is equal to alpha naught plus alpha 1 Pt, and now we have a new variable Ht. Ht may stand for the taste or habits of individuals. Now, demand would depend on what the taste and habits of individuals are. Similarly, if you look at the supply function, we have Qt, which is beta naught plus beta 1 Pt plus delta 2 Rt plus U2. In this case, delta 2 Rt is the new factor that comes in, and Rt is, we have assumed it to be rainfall. So, the supply depends on rainfall. For instance, what is the amount of wheat that is coming into the market? That will be defined by what the amount of rainfall is. So, we have a rainfall effect also. Now, in this case, you can very well see that Qt and Pt are endogenous variables. These are system variables which affect the system. Price affects quantity demanded, price affects supply, but then if the demand is high, then the price is going to go up. If the supply is high, then the price is going to go down. So, these are also affected by the system, and hence they are endogenous variables. Whereas, if you look at Ht and Rt, these are primarily exogenous by nature. So, taste and habit, they have an influence on demand, but demand does not have an effect on taste and habit. So, these are one way variables, similarly for rainfall, and therefore, they are referred to as exogenous variables. They are not affected by the system. So, this is how we first need to identify which variables are endogenous and which variables are exogenous. Now, when we set up the simultaneous equation model, we clearly distinguish between these two types of variables, and a general equation models would be written as follows. Suppose we have g endogenous variables in a system and k exogenous variables. Then the equations would lead like this. The first equation is beta 1 1 y 1 plus beta 1 2 y 2 goes up to beta 1 g y g. So, we have this part depending on the endogenous variables, and the second part starting with gamma 1 1 x 1 to gamma 1 k x k. This is the part which depends on the exogenous variables, and the sum of this is equal to some disturbance. Usually remember, we write the exogenous variables on the right hand side but in this case we have written everything on the left hand side, and I will explain why we do so as we go along. Now again we have a second equation involving the same y1 to yg endogenous variables and x1 to xk exogenous variables, and we have g such equations. In matrix notation, if we put this, we write the model as by plus gamma x is equal to u, where B is the matrix of the betas. So, B is a G by G matrix having the elements beta 1 1, beta 1 2, beta 1 g. These are the coefficients of the endogenous variables in the G equations. Y is of course the G endogenous variables, and we also have gamma, which is the coefficients of the exogenous variables x1, x2, xk given by the vector x, and then you have the vector of the disturbances. The question which naturally arises, and which you must have noticed by now, is that why do you have G equations? Why not 2, 4, 5 or maybe k or G plus k equations? There are G equations in G plus k variables y prime and x prime. Why G? This is because there are G endogenous variables in the system, and we can look up at this as each of these endogenous variables is a response variable in one of the equations. So, maybe the first equation has y1 as the endogenous variable. Assuming that beta 1, beta 2, beta gg equal to 1, we can write y1 as minus of beta 1 to y2 minus of dot dot minus beta 1 yj, and the x is x1, x2, xk, and then the disturbance component. So, you see that in this case we have made the first endogenous variable as the subject or the response, and the g minus 1 endogenous variables from y2 to yg as the independent variable along with x1, x2, xk. Similarly, in the second equation we can write y2 as the response variable in terms of the endogenous variables y1, y3, yg, and the exogenous variables x1, x2, xk. So, to write all the G endogenous variable as the response variable in one of the equations, we need G equations. That is the reason why we have G equations here. Now, the next question is why simultaneous equations? If you observe what we did before, and if you observe what we just did, y1 could be written in terms of G minus 1 endogenous variables and k exogenous variables. Similarly, for the other variables. So, the question is, why do not we treat the G equations separately? Why do we need to take them together in a simultaneous equation system rather than do G single equation regression models? And if we do that, it is easy because you can use the single equation techniques on each of them separately and get the estimates. The problem is that we cannot do that. There are two major reasons for that, and these reasons are because if we do that, we need to make very strong and unrealistic assumptions. What are the two assumptions we need to make? First of all, we need to make the assumption that the yj's are uncorrelated with the uj's. Which yj's? If you look at the first equation, then we have y1 as the response and y2 to yg as the independent variables along with the x's, of course. Remember, the x's are independent of u, so we do not have a problem, but the y's may not be independent of the u's. If they are not, then the estimates would turn out to be inconsistent. Remember, you have in your regression models studies have seen that the x's, the explanatory variables must be uncorrelated to the disturbances. In this case, yj's, some of the yj's are explanatory variables, and therefore they need to be uncorrelated to the UJs. Does this assumption hold? We will see. The second assumption that we need to make here is that the UJs are uncorrelated among themselves. So, if they are correlated, obviously we are losing some information if we are using them separately. So, if you look at one equation at a time, the first equation we have U1, and since the other equations are not there, the relationship of U1 with the other U's will not come in. Will that be a loss? Again, we will see this as we come along. First, we look at the invalidity of the first assumption. We say that this assumption is invalid in fact, so it is unrealistic to use this assumption. You see, y1 can be written as we saw, as minus beta 1 to y2 to minus beta 1 g yg, and in terms of the x's, and of course the u1 term. So, all the endogenous variables y2 to yg come on the right hand side as explanatory variables. Next, we look at y2. Again, y2 can be written in terms of y1, y3 up to yg, and then the x's plus u2. So, we are again making y2 the response here in the second equation, and we are expressing this in terms of y1. But now what we do is, let us substitute this y2 in the first equation. So, in the first equation, if we have this beta 1 y2 etc., from the first equation we take this and put this in place of y1 in the second equation, and therefore what we have is minus beta 2 into the whole expression for y1 and then the remaining terms as before. But what you observe in 2 is that y2 now depends on u1. u1 comes in through y1 to influence y2. It is there in the second equation. So, how can we say that in the first equation y2 and u1 are uncorrelated to each other? We see that they are related to each other. y1 influences y2 in the second equation. So, our assumption that y2 and u1 in the first equation are uncorrelated does not hold, and therefore, we say that this assumption is invalid. But then, as I said before, if y2 is correlated with u1, you know that the regression models will says that the estimator would be inconsistent. So, we cannot apply the ordinary least squares to get this parameter estimates. So, what we need to do, probably we can go for instrumental variable techniques etc., but it will bring in a whole set of complexities. So, that is an assumption we cannot make, and so very often we cannot treat the equations. Let us have a look at the second assumption. The second assumption I will not say is invalid, but it is more unrealistic, in the sense that what are the UJs? These UJs are the disturbances which are composed of several things. They can be pure measurement errors, they may be specification bias, they may be excluded explanatory variables etc. Now, if uj and uk contain the same excluded variables or the same specification bias, then they are bound to be correlated. What do I mean by that? Suppose I am looking at two commodities QT. One commodity is the consumption of meat or quantity of meat demanded, and the other commodity is the quantity of fish demanded. Now, obviously, this would depend on their prices, and we build up a model of quantity demanded on price and leaving everything else into the disturbance term. But then, if we are sampling from an area where we have vegetarians, so the quantity demanded of both would be less given the same prices. But if we are doing this from an area where there are more non-vegetarians, obviously the consumption should be more. So, what we see here is that there are some variables like whether a person is vegetarian or non-vegetarian, which will affect both the equations. But then we have not brought this variable in either of the equations. So, where are they? They are in the error part, and because the same variable is in both the error parts, these two errors would become correlated. So, we will see that very often the UJs are correlated among themselves, and if we do not take into account this correlation, then what will happen is that we will have less efficient estimators. So, the treating the equation separately would fail to take account of this correlation, and we would be losing a lot of information, which we would not like to do in a statistical study. So, what do we have now? Let us look at how we set up the model. We have by plus gamma x is equal to u, where we have defined b, gamma, etc. as before. We call this the structural model. This is the model with which we start. We will see there are other forms of this model, but these are the parameters we are primarily interested in, and we will call beta, b and gamma the structural parameters. Now, the assumptions that we have made up to this point is, firstly we will assume that b is non-singular. Why do you assume b to be non-singular? This is because, what is b? b is the coefficient of the y's. So, if two rows of b is the same, then it becomes a singular b. Okay. For b non-singular, it means that all the rows are linearly independent of each other. If not, then two equations becomes similar, and hence one of the equations can always be dropped. That is the reason when we have a really good model, b automatically becomes non-singular. We do not have any redundancy in the model, we do not bring in useless equations which will be similar to some of the earlier equations. So, b is assumed to be non-singular. Another assumption that we will make is x is non-stochastic, that is, the exogenous variables are non-stochastic, or if they are not non-stochastic, that is, if they are stochastic, they are at least uncorrelated to the error. As I have mentioned several times, this is required so that the estimators are consistent. Let us look at the error or the disturbance. The initial assumption is expectation of u is going to be 0, and the other assumption that we will make is the dispersion of u is a positive definite matrix sigma of the form sigma equal to small sigma 1 1, sigma 1 2, etc. Obviously, this matrix is going to be a symmetric matrix. What we are assuming here is that this sigma matrix is not diagonal. If it was diagonal, then the equations would have been uncorrelated, the errors would have been uncorrelated with each other, and probably in that case we could have used single equation systems to actually estimate the parameters separately without taking extra information from the other equations. So, we will be assuming that the sigma matrix is non-diagonal. This is the basic structure of a simultaneous equation model, and in the subsequent lectures we will go into more details about this model and see what the problems related to them are. In this lecture, we have introduced the simultaneous equation models. We have discussed what the cause-effect relationships are and what problem it causes in econometric studies. We have also discussed why we need to have simultaneous equation models. We have just introduced the model in this lecture and we have stopped there. So, in subsequent lectures, what we will be doing is we will be looking at the models in greater detail and look at the difficulties that this model creates and how to circumvent those difficulties. And we will also look at how to estimate the parameters of those models.